Hello, my name is YoungGyoun. I'm from KAIST, and today I'm going to talk about AccelTCP, which is a hardware-assisted TCP stack designed for better scalability and performance. And this is a joint work with my colleagues SeungEon, Asim, and my advisor KyoungSoo. So TCP is the most widely used transport protocol in modern networks, and many network applications today rely on TCP. And their performance becomes a key factor that determines today's network services. But at the same time, networking hardware is getting increasingly faster, but on the CPU side, we observe the slowdown or more slow. So now there's a clear gap between the growth rate of the network bandwidth and CPU. And that gap is only going to increase. So therefore, CPU efficiency of the TCP stack is now becoming more and more important. So to improve the CPU efficiency, there has been many recent works to optimize the packet I/O and bypass the inefficient kernel. But unfortunately, even with those efforts, there's still a fundamental barrier in TCP stack performance, which is TCP itself. So TCP is the single most expensive part of the networking stack, and as it needs to handle many complex operations, including connection management and data delivery. And in this talk, I'd like to discuss two cases where TCP overhead severely limits the application performance. So the first case is about short TCP connections, which are dominant in today's network. For example, in a commercial cellular network, we have 80% of CPU flows, which are very short, smaller than a kilobyte. And for every connection, TCP stack have to perform SYN and FIN handshake for every connection and to synchronize the connection states. But for the TCP servers, who has very short messages and short-lived connections at a high rate, this becomes a relatively huge overhead. So to quantify the overhead, we analyzed CPU usage on key value store, which is using mTCP, which is one of the state-of-the-art TCP stack. And we found that 60% of the CPU cycles were used for when there are short-lived connections are dominant, and they are only used for connection management. And another important class of TCP application today is layer 7 proxies, which is used to map client-side connection to backend server. And after establishing two connections and handling application headers, they often fall back to transparent proxy mode, which simply relay payload between two connections. But even for that case, the payload should be delivered all the way through the TCP stack and application, and this will bring a huge CPU overhead to reassemble TCP by stream as well as memory copy. So for example, for load balancer, which is working at 100 link, it needs to dedicate 48 CPU cores only for relaying the payload, which is very inefficient. So as a workaround, many existing network systems support a feature called connection splicing, which can be used to move the payload without any application involvement. However, even with this, there will be still DMA overhead as well as TCP overhead to reassemble the payload. So still we need lots of CPU cores to handle them. So as we observed in the two previous examples, CPU resources are heavily consumed by mechanical operations for TCP protocol conformance. And our good news is that we now see many smart NICs and programmable NICs coming up in the market, and this means we now have more computing power and memory resources near the network. So in this role, we propose to offload such mechanical and repetitive TCP operations to NIC so that we can improve the CPU efficiency of the networking stacks. But of course, TCP offload itself is not only idea, and there have been many efforts in this area, and I will highlight some of them here. So the first approach was proposed was full stack TCP offload, or TOE, which runs the entire TCP stack on NIC. However, this has failed to become popular because of two reasons. First, in order to perform entire TCP features on NIC, it has to maintain a large number of connection states for every connection. So NIC resources are much more restrained than the host. So if you think about that, it becomes easily becomes a bottleneck. And it doesn't scale well for the large number of connections. And second, having a full TCP stack in hardware makes it difficult to instance. So for example, in TCP, congestion control is one of the active area which is still developed. And there are many congestion control algorithms coming up. So if we move down the whole stack to NIC, it makes it difficult to evolve. So as a result, most NIC vendors are turning to offload simple fixed cost functions like TCP segmentation or like payload coalescing. And this benefit is but only limited to large size connections. So in this work, we are trying to extend the benefit of NIC offload to general TCP operations, including short-lived connections, as well as proxy applications. And we provide a new design point of rearranging the TCP stack features on NIC and host data plane to avoid any problems, which was occurred in previous NIC offload solutions. Okay, so now let's see how AccelTCP is designed. So AccelTCP is a dual stack TCP architecture, consists of NIC stack and host stack collaborating with each other. And we split TCP stack functionalities into two categories. First one is central TCP operations, which are subject to flexible policies or like require variable amount of CPU cycles. So most data transfer related features belongs to here, and because they have to handle many exceptions, for example, inferring the packet loss or handling the out of order packets. And so this logic is too complicated to run on the NIC data plane. And second, peripheral TCP operations, which are mechanical operations required to meet the protocol. So those operations are suitable for NIC offload because their logic is changed a little over time, and their processing cost is relatively small. So by offloading and separating out these peripheral operations from host, we can save more CPU cycles and use it for more valuable application tasks. But to bring a real benefit with this dual stack design, we had to tackle two major challenges, which is first, we should synchronize the connection states between the two stacks, and second, we need to avoid the NIC bottleneck. Okay, so let's first talk about the flow state synchronization. So connection management and splicing are basically stateful operations, so they need to track the flow states. So that's what we call transmission control block in TCP, so we call it TCP. And it makes the dual stack design challenging because now the NIC and host stack can both update the NIC, the TCP, so that we need to synchronize them across the different stacks. So if you think about the connection setup and teardown process, TCP states updates for every control packet, so it will end up with huge DMA overhead. So AccelTCP addresses this problem by enforcing a single ownership of TCP. So AccelTCP divides the connection management and splicing into separate phases, and at each phase, only either NIC or host will take the full ownership. So it means that the TCP sync will only happen in between different phases, so that we don't have to sync them all the time. And in addition, we allow the TCP sync messages. Such control messages can be piggybacked with the control packet, payload packets. And this is quite effective for small message connections. For example, if there's only one message transaction for the flow, it requires only 2 DMA operations to complete the entire connection. And the second challenge is about limited resources on NIC. So modern programmable NICs provide some fast memory, which can be used to program instructions and connection states. But their size is small, limited, and to like few megabytes. For example, Auxilio LX NICs only supports 8 megabytes of SRAM. And limited computing resources are another bottleneck. So typical TCP stacks spend thousands of CPU cycles to process a single packet. But if you push them down to NIC as it is, we expect to have 80% of performance drop in modern smart NICs. So to take the full advantage of the NIC offload, we introduced several different techniques to tame down the complexity of the NIC data plane. So for the first, in connection setup, we use sync cookie to make it stateless function. So, but to prevent any from any state explosion attack, we will need to use cryptographic hash functions. But luckily, today's smart NICs support them, which is optimized in hardware, so we can avoid the CPU bottleneck in the case. And second, connection splicing and teardown. For that case, we designed AccelTCP to offload only minimal TCPs required for each operation. So now NIC can handle 25 more connections than full stack offload. We also developed several different techniques, new techniques, to use compute capacity more efficiently. And in this talk, I'd like to introduce timer beam-map wheel approach, which is used for tracking timeouts. So in order to handle connection teardown and leak, we have to track multiple different timeouts. But tracking such timeouts at leak is not a trivial task. So modern smart NICs have hundreds of NIC cores, and they typically do not follow flow to core affinity because they want to do the load balance better. But it means that two different packets from the same flow can be delivered to different NIC cores. So so we need a globally shared data structure to track the timeout. But the problem here is that in a typical TCP flow, arming and disarming timer will happen multiple times for every connection. So under high connection rate, it becomes an expensive write-heavy operation, which makes a huge lock contention. So to address this problem, we propose a new technique called timer beam-map wheel approach. And basically, this is designed for efficient timer beam-map registration and unregistration and invocation in the NIC data plane. So NIC data plane now maintains a ring of beam maps which are ordered by the timeout value, and each bit on the beam map is a single flow indexed by flow ID. And I will give you an example. Let's say we have 3 flows which we have to track the RTO, and to add them to the timer, we simply go to the beam map whose timeout is like 8 milliseconds, and then mark the corresponding bits for the flow. And here, this marking operation is totally lock-free, so concurrent timer registration can be done in parallel by many number of cores. And as time goes by, timer will keep decrease, and when it reaches 0, we can scan multiple beam map and trigger the timer event. And in that case, we can also utilize hundreds of NIC cores at the same time to scan the beam map in parallel. So we also propose several interesting approaches to optimize the host stack optimization, stack as well. But I will skip them in this talk, due to the time limit. So please check out paper if you're interested. So now let me introduce how our system is implemented. As I described before, our AccelTCP stack consists of 2 parts, and our NIC stack is implemented on Metronome Auxiliary RX NIC. And this consists of P4 pipeline for packet parsing and C code for stateful operations. And we note that existing host network functions like NetFilter or IP tables can be easily added to this P4 pipeline. And for host stack, we extend MTCP to support NIC offload features, but basically we can easily extend other TCP stacks to work with AccelTCP by adding several small number of functions. And here's our setup for experiment, and then let's move on to evaluation. So we first present a micro benchmark result to see how much benefit AccelTCP can bring for short-lived connections. So we compare the throughput performance of the TCP server, which handles 64-byte messages for every connection, and we showed it throughput for a different number of CPU cores. And as you can see here, AccelTCP shows 3 times of performance gain compared to MTCP. So it shows the benefit of connection setup and teardown offload. But for the 8-core case, we observe the NIC bottleneck as the packet rate goes to very high rate. And one interesting point here is that AccelTCP shows comparable performance even if it is compared to MTCP's persistent connection performance, which does not do any connection setup and teardown. So because AccelTCP eliminates the connection setup and teardown process, overhead, and what it implies is that the application developers now don't have to stick to persistent connection because of the performance concern. So because now the complexity of handling the connection management is offloaded to NIC, so we don't have to take the complexity of handling managing connection pool or idle timeout. So with AccelTCP, you can just open up new connection whenever you need, and you can close it simply if you don't need it. And next, we evaluate AccelTCP real-world applications and see how much benefit AccelTCP can bring. So we first evaluate Redis key values for handling Facebook USR workload, where short-lived connections are dominant, and AccelTCP consistently shows 2.3 times better performance than MTCP in throughput. And this is actually comes from the AccelTCP's better CPU efficiency. So as you can see on the right side, we observe the AccelTCP's connection management design reduces the CPU usage into 1/4. And we next evaluate HAProxy, which is a widely used layer 7 load balancer on the realistic spec web workload. And AccelTCP provides more than 11 times better performance than MTCP's 8-core performance. And this implies that today's proxy applications were largely limited by DMA overhead as well as payload reassembly logic. So to summarize, we find that TCP requires many mechanical operations for protocol conformance, and our observation here is that for better TCP stack efficiency, it's better to utilize NIC resources to perform mechanical or repetitive operations of TCP, while more valuable host CPU resources can be used for more high-level application logic. And in this work, we explore a new design space to offload connection management and splicing to NIC, and we find that it brings a significant benefit to real-world TCP applications today. And our source codes are available at GitHub, so please check out if you're interested. So yeah, that's it for my talk, and thank you.
Bravo. 18-minute talk in 16 minutes. You get 1 more minute. But yes, you can set up. OK, questions?
I have a question, actually. So in normal kernel stack, actually, between the NIC and the TCP, there's a bunch of different packet processing hooks or the IP filters, right? So how does that work if you offload the TCP state into the NIC? How do you handle those packet processing hooks?
So let me phrase your question. So your question is about how NIC handles the complex states of the for the teardown process?
No. I'm talking about those IPTP filters, right? So in a normal kernel stack between TCP and the NIC, there's a different kind of filters. People adding a bunch of filters, right, in the middle.
Okay.
Right?
BPF filter or IP tables or like that
yeah,
filter?
maybe eBPF, right? So
yeah,
something like that.
Okay.
So how do you actually handle that?
Okay. So actually, as I introduced in our implementation, we have P4 pipeline in front of AccelTCP at NIC. So in the case of, in order to offload the TCP connections, we have to handle the pipeline, packet filter pipeline in front of the TCP stack, right? So in that case, we have to offload that filter logic to the networking stack. But luckily, we have a P4 pipeline in modern smart NICs, so we can easily add in that filter to the P4 pipeline in front of the AccelTCP NIC stack.
No, the problem is actually, for example, eBPF may have user programs, right, which is written by the users. Mm-hmm. And how do you actually handle that?
But, as far as I know, there are many smart NICs which can compile the eBPF kind of program into some program which can run on the NIC data plane. So you
okay.
Yes. So yeah, many NICs support that. So you can simply use that, and and AccelTCP will totally work with that.
Okay. Yeah, we can talk offline.
Okay.
Yeah.
Hi, I'm Kizzy. I really like your work. So it seems like the accelerator TCP works very well when there are lots of short flows. Mm-hmm. But for the long flow case, it seems like the performance is very similar as MTCP. Is that right?
Yes. For long flows, our MTCPs, if we compare the performance of MTCP and AccelTCP for long side flows, the performance will performance gain will diminish as the flow size will increase. So
I see.
for that case, we don't have, but we still support TCP segmentation offload and large receive offload, so we can still get that benefit. But besides that, we don't have any benefit.
Cool. Thank you.
Thank you.
I have one question for you. Do we have a very good understanding of where the CPU bottlenecks are after we use AccelTCP? So you talked about how DMA was one of the CPU bottlenecks before using AccelTCP.
Yes,
Do we
yes.
have a very good understanding of where the current bottlenecks are after we start using some of the work that you proposed?
Okay. So like as I, so
If somebody were to improve upon your work or try to improve upon your work, what bottlenecks will they need to be resolved?
So after we offload the connection management and splicing part to NIC, like that kind of things will like go away. But even in TCP stacks still have to do something. Like for example, data delivery part is one thing. So in that case, we can think of like optimizing the data path of the like command send and receive on the host stack. That's one thing I think. So. But,
Good, thank you. Let's thank the speaker again.
Okay.